Hello everyone, welcome to my YouTube channel SGKmistry Lectures. In this video, I'll be explaining the acid-base chemistry in which I'll be covering the concepts of acids and bases, the factors affecting the acidity as well as the basicity, and also we'll be covering on hard soft acid-base concept, that is HSAB concept. Along with that, we'll also be discussing on the non-aqueous solvents. So now let us try to understand about the various concepts of the acids and bases which have been given. So before that, several definitions of acids and bases have been proposed from time to time. So because of which there is a confusion with respect to what are acids and what are bases exactly, right? So each definition is correct with respect to its own framework, and therefore we need to apply the one which is most suited under whatever the circumstances we are considering, right? So now when I'm talking about the first concept, one of the first successful concept in explaining about what are acids and what are bases is the Arrhenius concept. So according to Arrhenius concept, the acids are the substances which give H plus ions in aqueous solutions. So for example, if I take HCl as the acid, so what happens in aqueous solution? You're going to get H plus and Cl minus. So it is very clear that HCl is an acid because it forms H plus ions in the aqueous solution. When we are talking about bases, these are the substances which give OH minus ions in aqueous solution. So the simplest example I can take is sodium hydroxide. So it can form Na plus and OH minus. So this was proposed by Arrhenius. And when we are thinking about the process of neutralization, so we know that neutralization is where the acid and the base react together to give the salt and the water, right? We know the definition of neutralization now, but as given by Arrhenius, the process of neutralization is again the acid and the base, they react together. So we know that water is produced as one of the product, along with that the salt is produced. But now since we are mainly concentrating on these H plus and OH minus ions, so the neutralization process was explained as the reaction between H plus and OH minus ions to give water. So this is how the neutralization takes place according to the Arrhenius concept. So the next successful theory is the Bronsted-Lowry concept, where the acids were defined as proton donor species, whereas the bases were considered as proton acceptor species. Right. So now if I consider H2O plus H2O, that is the solvent, so it can give rise to H3O plus and OH minus. So one of the proton can be transferred from one water molecule to the other. So the one which donates the proton, it acts as the acid. The one which accepts the proton acts as a base. So here, in this case, if I'm taking here, this is the solvent, right? And here, now in the product side, we have H3O plus and OH minus. So it is very clear that H3O plus can lose a proton. So this is the acid, and OH minus can accept a proton so that it forms H2O. So this is a base, right? So I can also take some other examples like NH3. Again, NH3 as a solvent, if I'm considering. So you can get NH4 plus. Along with that, if one proton is lost, you get NH2 minus. So in the product side, now it is very clear NH4 plus can donate proton. So this will be the acid. Now this will be the base because NH2 minus can accept a proton and become NH3. So I need to take 2 moles here because of, so that it is balanced, right? Same way I can also take HF. So what happens is, again, this can form H2F plus. Along with that, you can also get F minus. So again, I need to take 2 here. So this is again acting so as a solvent. And in the product side, now it is very clear H2F plus can donate a proton. So this acts as an acid, whereas F minus can accept a proton. So this acts as a base, right? So now when we are considering the conjugate acid-base pair, so here, these are the species which differ from each other only in the terms of the transferred proton, right? So now we have the examples for conjugate acid-base pair. Already we have written the equations. So now suppose I take this example HCl plus NH3. So it is very clear that HCl, the H plus from HCl is transferred to the NH3. So the NH3 is converted to NH4 plus and HCl is becoming Cl minus because of the loss of a proton, right? So in the reactant side, we know that HCl is donating the proton. So it is a proton donor species. So without any doubt, this is the acid. And NH3 is accepting the proton. So this is a base. In the product side, if you are looking into detail, so we know that without any doubt, we know that NH4 plus can donate the proton now and Cl minus can accept the proton. So NH4 plus is nothing but the conjugate acid. And Cl minus can accept the H plus. So this acts as a conjugate base, right? So one more thing you need to remember, the strong acid has always a weak conjugate base. A weak acid has a strong conjugate base. So this is one simple rule we need to remember when we are talking about the Bronsted-Lowry concept. So this is with respect to Arrhenius as well as the Bronsted-Lowry concept and the definitions, right, with base, on the basis of acids as well as bases. Now let us talk about the acid-base concept in the non-aqueous media. So whenever we are talking about the behavior of the solutes in the non-aqueous solvents, it is often regarded in terms of the solvent system concept. Okay, so this definition, it mainly depends on the mode of the self-ionization of the solvent, and each solvent is considered to be the parent of the acid as well as the basic species. So again, when I'm talking about the solvent, so self-ionization takes place because of which you're going to get the cationic and the anionic species like that of the water. We have seen it in water, right? How the hydronium ion as well as the OH minus ions will form. So similarly, we can also consider this in other non-aqueous media, the other than water. So those solvents also can undergo self-ionization to give one cation and one anionic species. So based on this, we can say the acid is nothing but a solute that directly or indirectly increases the concentration of the solvent cations, whereas the base is the one which increases the concentration of the solvent anions. So let us look into the example. So now suppose we take the NH3. So this we have already written in the previous concept. So we know that NH3 self-ionization takes place. It gives NH4 plus and NH2 minus, right? Then we also have, we can take SO2. So SO2 can give SO2 plus, along with that SO3 2 minus. So a positively charged ion as well as a negatively charged ion will be formed because of self-ionization, right? Similarly, I can also take HF. So this also we have written in the previous concept. So H2F plus and F minus can be formed. Now, let us take the example of now ammonium chloride, right? So NH4Cl. Let us try to understand about the behavior. So ammonium chloride, it forms NH4 plus ions, right? NH4 plus ions as well as Cl minus ions in the solution, right? Now it furnishes NH4 plus ions. Now suppose you're taking it in ammonia solution. So ammonium chloride NH4Cl in ammonia solution if you're considering. Here we know that the NH4 plus ions are formed. So this increases the cations, right? So ammonia on self-ionization, it forms NH4 plus and NH2 minus. Now this ammonium chloride, it furnishes NH4 plus ions, so which are cations, which are characteristic of the solvent. So because of self-ionization of ammonia, we have this NH4 plus ions that are formed, and also the concentration of these cations are increased because of NH4Cl, the dissociation of ammonium chloride, right? So because of that, the NH4Cl in ammonia, it behaves as an acid. This is how we define acid in the non-aqueous media. So let us talk about KNH2. So again, KNH2, potassium amide in NH3 again, right? You can also consider sodamide, NaNH2, right? So KNH2 in NH3. So we know that KNH2 will form K plus NH2 minus, right? And ammonia on self-ionization, it forms NH2 minus anion. And it is very clear that KNH2 will form NH2 minus anion. It increases the concentration of the solvent anions. So because of which this KNH2 acts as a base. I hope it is clear how we are going to decide about the behavior of the various solutes based on the concentration of the solvent ions. So whether it increases the concentration of the positive ions or it increases the concentration of the negative ions, then we decide the nature of the particular solutes. So now suppose we are talking about neutralization in this case. So suppose we take NH4Cl plus KNH2. So in the presence of ammonia solvent, so you're going to get KCl, and here NH4 and NH2 are there. So which combine together to give two ammonia molecules. So here this is the solvent again. And here you get the salt. Now since we are performing this neutralization reaction in ammonia solvent, you're going to get the ammonia solvent as one of the product. Right. So then we have this acts as a base and this acts as the acid. So just in the previous slide, we discussed why KNH2 acts as a base and why the ammonium chloride acts as an acid. Next, coming on to the Lewis concept. So again, this theory, it is mainly based on electron pair donation as well as acceptance. So according to this theory, the acids are the species which accept an electron pair. So it has a tendency to gain electron pairs. So, or other words, I can also call it as electron pair acceptors. And mainly how they accept these electrons, because they have the vacant orbitals which help them in accommodating one or more electron pairs. Right. When I'm talking about bases, these are the species which have a tendency to donate the electron pair or electron pairs. Okay. And also such species, now how they can donate these electron pairs? Because they have the unshared electron pairs or the unshared or lone pairs of electrons on the atoms. So because of which the bases can donate that particular electron pair. Now, the acid-base or neutralization reactions can be termed as donor-acceptor reactions, or it can also be termed as coordinate covalent bond formation reactions. Because here we are mainly considering the donation of the electron pair from the electron donor to the electron pair acceptor. So we can write it in general as acceptor plus donor. So acceptor here, the electron pair acceptor is the acid, electron pair donor is the base. So it can give rise to the donor acceptor compound. Or you can also call it as a neutralization product. Neutralization product. Right. So we can take a few examples to understand this better. So suppose we have BF3 and you're going to treat it with NH3. It is very clear that nitrogen has a lone pair of electrons. That is, in ammonia, we know that nitrogen, because of the lone pair of electrons, it can donate this lone pair of electrons to BF3, especially the boron that is present here. So NH3 and BF3. So a particular donor acceptor compound is formed, and here it is mainly the BF3 which is acting as an acid and ammonia as the base. Similarly, we can also take SnCl4 plus R2O. So with the ether, so again, ether, the oxygen has lone pairs of electron. So SnCl4. So here we are going to take 2 moles. Similarly, you can take H plus NH3. So H plus it can accept the pair of electron, whereas NH3, it has an electron pair. So because of which you can also write that NH4 plus is formed. Similarly, I can also take FeCl3 plus Cl minus. So FeCl3 acts as an acid, Cl minus acts as a base, so we can get FeCl4 minus. Similarly, SO3, sulfur trioxide, and here we have the peroxide ion. So you can get SO4 2 minus. Right. This is with respect to what are acids and bases according to the Lewis concept. Now, talking about the classification of the Lewis acids. So again, based on this, we can write it with 2 different headings. See, all the cations, when we are talking about in case of Lewis acids, they have a tendency to accept electron pairs. So whichever cations can accept the electron pair, so those are called as Lewis acids. Right. So when we are talking about examples, the small cations like H plus, Li plus, B2 plus, so they are very strong Lewis acids, again, mainly because of their high tendency to accept electrons and they form the stronger bonds, right? Again, when I'm talking about the larger cations, such as the alkali as well as the alkaline earth metals, the cations, so they behave as weaker Lewis acids, mainly because of their less tendency to accept the electrons. Okay, so next, talking about the higher charged cations, they have a higher tendency to accept electrons when compared to that of the lower charged cations. So these are the different factors that have to be kept in mind when we are deciding which cations can act as better acids. So mainly the size of the cation should be smaller as well as the charge on the cation should be higher to make it as a stronger Lewis acid. Now, let us look into certain examples to justify these different conditions. So suppose you are talking about Fe3 plus. So the charge is plus 3 here. Let us compare it with Fe2 plus. So Fe3 plus, which has a larger amount, the magnitude of charge, it is a higher charge cation. So it behaves as a stronger Lewis acid when compared to that of the Fe2 plus. So here it is stronger. Fe3 plus is a stronger Lewis acid. Next, if I'm comparing SN4 plus as well as SN2 plus, obviously SN4 plus is a stronger Lewis acid than SN2 plus. So again, it is mainly because of the higher magnitude of the charge, right? So next, let us look into the cations, like how they act as Lewis acids. So let us take the example here, Ag plus, when it is reacting with NH3. So here, this is the Lewis acid. And here we have Lewis base, right? So complex formation takes place. So you're going to get Ag, NH3 twice plus, right? Now, if I'm talking about the geometry of this complex, we know that it is linear. There are two ligands here. So obviously, these two ligands are going to arrange around the central metal ion to form a linear geometry for the molecule. Similarly, if I'm going to take Cu2 plus, which acts as the Lewis acid, it can combine with fluoride ions. So to form CuCl4, 2 minus. So I'm going to balance the equation, 4Cl minus. So there are 4 chloro ligands and here the geometry is tetrahedral. Next, you can also take other examples. Manganese in the presence of water as a ligand. So you're going to get manganese, H2O 6 times, 2 plus. So there are 6 ligands here. So without any doubt, we can write it as octahedral. So here I'm going to write 6H2O. You can also take other examples like nickel, 2 plus, and with the cyanoligand. So we have Ni, CN4, the charge will be 2 minus, right? Because Ni2 plus and there are 4 cyanoligands, so total charge will be minus 2. And here the geometry is square planar. So this is with respect to the cations which can act as Lewis acids. When they react with the Lewis bases, they can form various complexes. Next, coming on to the electron deficient compound or the compounds in general, in which the central atom, when the central atom can expand its valence shells, right? So they can also behave as Lewis acids. So let us take the example where we have BF3. We can also talk about AlCl3, or you can take the example of GaBr3, etc. So these are the compounds. They have a tendency to accept the electron pair so that they can complete their octet. We can take the simple example of BF3 to understand this better. So we know that boron has atomic number 5. So we have 1s2, 2s2, 2p1. Right. Now, we know that there are 3 electrons in the valence shell, which form 3 bonds with the fluorine atoms, but it doesn't have an octet. Although BF3, the molecule is formed, but the boron, that is a central atom that is present in this molecule, it does not have an octet of electrons surrounding it. For example, I can write it as here BF3 plus F minus. It can result in the formation of BF4 minus, right? Similarly, if I'm talking about the compounds, let us say SiF4 or SnCl4 or you can take SbCl3 or SbCl5. So such compounds where the central atom can expand its valence shell. So it represents the Lewis acids. So we have the examples here. If you take SnCl4, so the ligands, so it can form Sn. So already there are 4 plus 2, so 6, and charge will be -2, right? Next, I can also write the equation for SiF4. Again, it can take up 2 more fluoroligands to form the complex. So SiF6, 2 minus. Okay, so these are with respect to how the electron deficient compounds or the ones which can expand their valence shell, they can act as Lewis acids. Next, coming on to the classification of Lewis acids. So first of all the anions which have a tendency to donate the electron pairs, they can act as the Lewis acids. As per the definition itself, we know this. Next, talking about the species which have the lone pair of electrons, they can also act as Lewis bases. So we have examples here. I can write it as the oxide ion. You can also take hydroxide ion, halides. So all these are coming under this particular category where these are anions and they can donate the electron pairs. Similarly, the neutral species, but still they have the lone pairs, so they can also act as Lewis bases. So for example, water, oxygen has lone pair of electrons on it. Ammonia, right? Then we can write ethers. Again, oxygen has lone pair of electrons on it. Then we can also take RCOR, the ketones where oxygen, again, it has lone pair of electrons. So such molecules which are neutral and still there are lone pairs of electrons that are present in the atoms, so they can also behave as Lewis bases. So this is with respect to the classification of Lewis bases. Next, coming on to the extended Lewis concept. So the extended Lewis acids, mainly they include coordinatively unsaturated species. So for example, we have carbon dioxide or CS2, where the central atom is bonded to atoms of different electronegativities by one or more multiple bonds. So here we know that very clearly the carbon dioxide, it has this particular structure. So it is bound to 2 oxygen atoms again by making use of multiple bonds. Right. So this is mainly because of the fact that the pi electron cloud of these carbon dioxide or CS2, carbon disulfide. So this pi electron cloud gets polarized whenever the Lewis base is approaching these molecules, especially when the Lewis base approaches the carbon of these molecules. Okay. So because of this polarization, it leads to the partial positive charge on the carbon as well as obviously there is oxygen or the sulfur that is present here. So mainly because of the polarization, carbon gets the partial positive charge, whereas the oxygen or the sulfur, they get the partial negative charge. So now the positively charged carbon, now it acts as an electron acceptor, and mainly it can accept the electrons from the Lewis bases. So because of which we call this carbon dioxide as a Lewis acid. We can take the example. So we have carbon dioxide. Now this is treated with, let us say, the hydroxide ion. So now the carbon can act as the electron acceptor. So this bond can shift here. So because of which you can get C double bond O, here O minus, here we have OH, right? So now this is nothing but HCO3 minus, which is nothing but the bicarbonate ion. So mainly the extended Lewis bases when I'm talking about. So here it can be the species like carbon monoxide or the unsaturated hydrocarbons. Okay, so it can be alkenes, alkynes, benzene, such unsaturated hydrocarbons. So why do we consider them as Lewis bases? Mainly because of the donation of the lone pair or mainly these hydrocarbons, they form the pi complexes with the metals when the metals are in their low oxidation states. Okay, so again, when I'm talking about the Lewis base, it shows dual characters of the donors as well as the acceptors. So let us take into consideration nickel plus carbon monoxide. So now here we have nickel and carbon monoxide. Nickel is the metal, right? And the carbon monoxide can act as a Lewis base. So because of which you can get NiCO4, right? Nickel tetracarbonate. Similarly, iron, it can also combine with carbon monoxide where it can form iron pentacarbonate, right? Similarly, chromium with benzene, it can also form complex, so C6H6, twice, right? So here we have 2 benzene, right? So diphenyl chromium can be formed by the reaction of benzene with chromium. Next, coming on to the applications of the Lewis concept. So mainly it describes an acid-base behavior as independent of the presence or absence of specific elements. Like it is not mentioning that H plus should be present or OH minus should be present, nothing like that. It the whatever the definitions are given, it is independent of all these the specific elements or groups or the ions that are there, and it does not involve the presence or the absence of any solvent mainly, right? It does not require the presence of a solvent. So because of which this makes the Lewis definition very advantageous as well as highly applicable, right? Next, coming on to the limitations of the Lewis concept, it is not going to give us any uniform scale of the acid or the basic strength, right? It just tells what is an acid or what are bases, but it's not giving us how to decide what are the factors which will affect the strength of the acids or the bases. Along with that, it does not even tell us whether the salt formation is again related to the acid-base behavior or not. Right. Next, talking about the normal acid-base reactions. Usually they are fast, but here it considers the acid-base reactions as donor-acceptor complex formation, but usually the donor-acceptor complex formation reactions are slower, right? And again, it is very general, and even the formation of nickel tetracarbonyl as well as diphenyl chromium, all these are considered as Lewis acid-base reactions under this particular Lewis concept. But however, the bonding that is involved in these complexes, it is again much more complex, and it cannot be explained very clearly by making use of the Lewis concept or the Lewis acid-base theory, right? So for this sake, let us now try to understand a much better concept, that is the hard and soft acids and bases concept, that is HSAB concept. So next, talking about the formation of a stable complex between the vacant orbital of an acid as well as the filled unshared orbitals of a base. It can be the ligand, right? It depends upon the nature of the metal ion as well as the ligand. So we know in case of the complex formation, mainly the ligands are the donor of the electron pairs. So based on this, Pearson suggested a simple rule, okay, which is nothing but the HSAB principle, which will help us in predicting the stability of the coordination compounds, right? So mainly here also, we are talking about the acids, which are classified as hard acids and soft acids, and bases, which are again classified as hard bases and soft bases based on the different criteria. So let us look into how we are going to understand about the different classes of acids and bases, right? So first, coming on to the metal ions. Metal ions can be again classified into class A metal ions as well as class B metal ions. So let us talk about class A metal ions. These are nothing but the alkali as well as the alkaline earth metal ions. Alkali and alkaline earth metal ions. And along with this, there are also the lighter transition elements which can be considered under this category. So for example, we can write Ti4 plus, chromium 3 plus, Fe3 plus, all these come under class A metal ions. Now, what are these class B metal ions? So these include heavy transition metal ions. So we know that in class A metal ions, we are only going to take the lighter transition elements. So in class B, we are going to take the heavier transition elements. Transition element ions or transition metal ions. So for example, we have PD2 plus. So mainly we are going to consider the ions of the second and the third row transition elements. That is the 4D and the 5D metal ions. So PD2 plus, you can take PT2 plus, cadmium 2 plus. So these are a few examples. As well as we can also consider the lower oxidation state ions like the Cu plus as well as Ag plus, Hg plus, etc. So these are considered under class B metal ions. Next, talking about the bases. So the ligands are considered as bases, of course. And here again, we have class A ligands as well as class B ligands. So the class A ligands include the molecules or the ions where the donor atom is nitrogen, oxygen, fluorine, chlorine, or in other words, I can say that here, mainly the donor atoms are of high electronegativity. When we're talking about class B ligands, so here the donor atoms can be like P, As, S, Se, right? Sulfur, phosphorus, selenium. So all these. So here mainly the atoms, the donor atoms, they have lower electronegativity, right? So now based on this, the hard bases are the ones which are considered. So hard bases and hard acids are the ones which are considered under class A, right? And whatever we consider under class B, the class B bases as well as the class B acids, so those are considered as the soft acids or the soft bases, right? So this is one basic idea. So whatever was considered under class A, so those are considered as hard. So class A metal ions as well as class A ligands are hard acids as well as hard bases respectively. Similarly, class B, so metal ions as well as the class B ligands are considered as the soft acids as well as soft bases respectively. Okay, so this is one basic rule you need to remember. So now, when I'm talking about the class A acids, so we know that these are hard acids, right? So now we have the examples like lithium Li+. We know that they are alkali metals or alkaline earth metals or the metals of the lighter transition elements or the transition metals, right? So we have Be2 plus or aluminium, Al3 plus, chromium 3 plus, etc. So these are under the class A acids. Now here the cations, they have smaller size and they are lighter elements. Again, they have high charge. So size is small as well as charge is higher. So this we have already seen that whenever the size of the cation is smaller as well as the charge is higher, then it acts as a good acid. All right. So you cannot easily polarize these cations. Along with that, the molecules or the ions with lesser number of valence electrons. Right. Here we know that they have less. These are the molecules with lower valence electrons. Next, talking about the second category, that is class B acids, which are nothing but the soft acids. So we know that already these are the cations which we are taking from the higher or the heavier transition elements, right? So for example, we have the Ag plus with low oxidation state, then we have Pd2 plus or Pt2 plus, right? So it is very clear that they are of larger size or they are heavier elements. And here the charge is lower when compared to that of the hard acids. And because of the lower charge as well as the larger size, mainly because of the larger size, they are easily polarizable. And mainly here we know that these are the molecules or the ions with larger number of valence electrons. Next, talking about the third category, that is the class A bases, which are nothing but the hard bases, right? Whatever is under A, they are hard. So we have examples where the donor atoms are highly electronegative. So we have H2O, then we have NH3, right? Then we can also take F minus. So all these comes under hard bases. So again, we can easily look into the properties of these hard bases. So here the donor atoms are having very high electronegativity. So here mainly the polarizability is lower. Now talking about the class B bases, which are soft bases, right? So here we know that the donor atoms, they do not have higher electronegativity, they have low electronegativity. So we can take different examples. So I minus, thiocyanate ion. So these are a few examples. So it is very clear here. They are having lower electronegativity, especially the donor atoms. And again, the polarizability is higher because of the larger size. And again, the electronegativity is lower, so the polarizability will be higher. So now talking about the acids and bases, we can, based on this HSAB concept, we can write the different examples. So hard, soft, as well as there are also borderline acids and bases. So let us take a few examples. So let me write a few examples for acids as well as for bases. So we have here. So here under hard acids, very important as well as common examples are H plus, then we have Li plus, sodium, right? Potassium, these alkaline earth metals and alkali metals, metal ions, all these are under hard acids. So Be2 plus, Mg2 plus. We can also take calcium, Ca2 plus, aluminium, right? Then you can also take other transition metals such with the higher charge, right? Zirconium, titanium. So especially the lighter transition elements. Then you can also take the other hard acids like SO3, carbon dioxide, BF3. So these are a few other examples. Okay, HX, AlH3, etc. So similarly, under soft acids, we can write the Cl, Br, I, iodine, bromine, right? Then we also have Br plus, then we can write BH3. Then we can also take the heavier transition elements like CD2 plus, Hg2 plus, right? Copper with the lower charge, Ag plus, again with lower charge, Au plus, etc. Right? Pd2 plus. So these are a few common examples. Next, borderline acids, you can also write SO2. We have NO plus, Sb3 plus, right? Then bismuth with a 3 plus charge, SN2 plus, Pb2 plus, zinc also comes under borderline, copper 2 plus. So all these are considered under borderline acids. Next, talking about the bases. So hard bases are the ones in which the donor atoms are having high electronegativity. So I can take the examples here, NH3, N2H4. Then we have primary amines, RNH2, alcohols, ROH. You can also take ethers, right? Then even ketones. Then we can also take anions like F minus, Cl minus, then nitrate, sulfate, etc. Okay. So similarly, you can also take soft bases where we have different donor atoms, again, which have lower electronegativity. So C2H4, C6H6. So unsaturated compounds also you can take under this. So RSH. Then we have R2S. Then we have the anions, Cn minus, right? I minus, hydride ion. So R minus, again R3P. Okay, so trialkyl phosphine. So all these examples also can be taken under this, right? Next, talking about the borderline. So we have C6H5NH2, right? That is aniline. Then we can also take C6H5N. Then we have nitrogen, NO2 minus, SO3, 2 minus, bromide. So all these are considered under borderline bases. Next, talking about the HSAB principle. So what exactly, how the acid-base reaction takes place and how the compounds are formed, right? So according to this, mainly the hard acids, they prefer to bond with hard bases, and the soft acids, they prefer to bond with the soft bases. Now, again, hard acids and hard bases, they are not easily polarizable, and their interaction are mainly ionic in nature. Whereas soft bases and soft acids, we know that they are usually polarizable, and because of which their interactions are predominantly covalent in nature. So this is the basic rule we need to keep in mind when we are talking about the HSAB principle. So hard bases, mainly we can take examples like ammonia or water or F minus. They usually combine with hard acids, right? For example, like Fe3 plus or Al3 plus. So mainly we know that hard acids and hard bases, they combine with each other. Whereas if you're taking the examples of soft bases like R3P, or it can be R2S, right, or I minus. So mainly they prefer to combine with the Pt2 plus or Pd2 plus, platinum, palladium, or mercury, or Ag plus. So which are the heavier transition metal ions, or the ones which have lower charge. So mainly again, they form complexes. Okay. So mainly when you're talking about the hard acids, they show this particular order for the preference of binding the donor atoms. So here we have F minus, it shows the maximum binding capacity. Then we have Cl minus, then we have Br minus, then I minus. And also we can say R2O, which is having the higher capacity when compared to that of the R2S. Similarly, I can also write it for R3N, which is more preferred when compared to that of the R3P. Talking about the soft acids, they show the opposite trend to the hard acids, mainly in this order. So I can write it in this order. I minus will be maximum, then Br minus, Cl minus, as well as the F minus. Then again opposite, R2S will be greater when compared to the R2O. Then again R3P, which will be much higher than that of the R3N. So this is with respect to the soft acids, which show the opposite trend to the hard acids for binding with the donor atoms or the ions, right? Talking about the applications of the HSAB principle. So first coming on to the stability of the complexes. Now, when I'm talking about the complexes which are formed with hard, and soft preference, they are more stable when compared to that of the hard, soft complexes. So mainly this HSAB, this particular principle can be used to predict the stability of these complexes which are formed between the different acids and the bases. So let us take the example. Here we have Ag plus. It is clearly a soft acid, right? If it combines with I minus, it is very clear. So let me write this is soft acid. We know that this is a soft base. Let me write Sb. So here it forms Ag, I2 minus. So this particular complex is stable, right? Because it is formed by the combination of soft acid and soft base. Similarly, let us take one more example. So Ag plus, now if it combines with the hard base, so fluoride is a hard base, right? So this is hard base, this is a soft acid. So here what is going to happen? You are going to get AgF2 minus, which is unstable. So mainly here, why it is unstable? Because of this particular complex is formed by the interaction between the soft acid and a hard base. So it's not soft or hard complexes which are formed here. It is here, it is between the soft and the hard, that is soft acid and hard base, because of which this particular complex is unstable. Next particular application of the HSAB principle. So course of the reaction can be predicted. So let us look into the examples. Okay, so again here hard and hard, soft and soft combinations. The products that are formed by these combinations are more favored. So let us look into the examples. So let us take lithium iodide. So lithium is hard acid and iodide is a soft base. So this is nothing but hard soft combination. Now you take and treat it with cesium fluoride. So cesium is a soft acid and fluoride is a hard base. So again, soft hard. Now it is easily predictable what are the products that will take place and why the forward reaction is favored. So it will lead to the formation where hard and hard will combine together. So you get lithium fluoride where it is hard and hard, right? Along with that, you get cesium iodide. So here it is soft and soft, right? So similarly, I can also take other examples like here calcium sulfide. So it is very clear calcium is hard and sulfide is soft base. Calcium is a hard acid. Treat it with water. So water is a hard base, right? Because oxygen is a highly electronegative atom. Whenever the donor atom is highly electronegative, then those bases are hard bases. So we have here calcium oxide, which is again hard and hard, right? Calcium is a hard acid, oxygen oxide is a hard base. So along with that, you have H2S as the product, right? So similarly, you can also take other examples, CuI2 plus CuF, right? So this is nothing but here we have copper, hard, and iodide is soft. Here we have copper, which is soft because it is in the +1 state. So it is soft. And then the fluoride is hard. In the first case, copper is in the +2 state. So that's why I've taken it as the hard acid. Whereas in CuF, copper is in +1 state. So obviously it is considered as the soft acid, right? So here you're going to get the product CuF2 because both are hard. Along with that, you're also going to get CuI. So let us balance the equation. Yes, CuI, which is nothing but soft, right? Cu2 plus, as here it is Cu2 plus, which is hard. And here it is Cu plus, which is soft. So based on that, we are going to get This is the reason why all these reactions, they proceed towards the forward direction, mainly because of the formation of hard as well as soft compounds. That is because of these combinations which are more preferred. Right. So next, coming on to the classification of the acids and bases. So mainly the acids and bases are classified as hard or soft, mainly depending on their behavior in the particular equilibrium, how the reaction is favored, whether the reaction moves forward or the backward reaction or the reverse reaction is favored. So first of all, if the base is a soft base, then the reaction with the soft acid, if it takes place, then usually what happens is always the product, the forward reaction, that is for the formation of the product, will be favored. So we are going to get the respective products. So let us look into the example. So B minus H plus. So we know that H plus is a hard acid and B is a soft base, B minus. So then we have CH3, Hg here plus, which is a soft acid. So you're going to get CH3, Hg plus, here B minus. Along with that, H plus is removed off. So we know that this is a soft acid and this B minus is a soft base. So both of these will combine together, and in this case, the forward reaction is favored, right? So similarly, you can also take other examples. Now we have AF minus, right? So A plus is nothing but in this case, this A plus can be any of the soft acid. Okay, for example, it can be Ag plus or something like that, which is a soft acid. So F minus is a hard base. We know that. So if it is treated with SCN, that is thiocyanate ion, which is a soft base. So this A is nothing but, as I already told, it is a soft acid. So you are going to get A plus SCN minus, right? Or ASCN. That is, if you're taking Ag plus, you get AgSCN. Along with that, F minus is removed off, right? So this is how we are going to decide how the soft and soft interactions or hard and hard interactions will lead to the forward reaction in case where there is a possibility of these combinations. So next, coming on to the occurrence of ores and metals, that is ores and minerals specifically. So again, hard and soft interactions. Over the hard soft interactions, it influences the occurrence as well as the formation of these important ores as well as the minerals. Okay, that is what is important to be remembered, mainly in the Earth's crust. So again, it is based on this hard and soft interactions. Now, for example, when we are talking about these Na plus, K plus, Mg2 plus, which are all hard acids, right? Ca2 plus, or I can take Mn2 plus or Cu2 plus, which are hard acids. They occur as their oxides or they may occur as their carbonates. Okay, oxides is O2 minus, carbonate is CO3 2 minus, or they can also occur as their halides, right? So halides X minus. So mainly we know that all of these oxides, carbonate as well as halides, they are hard bases, right? Which have the donor atoms with high electronegativity. So now we also know that these are hard acids. So especially when they are even present as ores or minerals in the Earth's crust, they are in the form of hard and hard combinations. So in the same way, I can also take soft acids, for example, Cu plus, or it can be Ag plus, we can take Hg2 plus, or you can take cadmium, Cd2 plus, etc., which are again soft acids. So they occur as their sulfides, okay, S2 minus, or it can also occur as iodides. So mainly here, if I'm talking about halides, we are talking about chlorides as well as fluorides. But here we know that iodide is a soft base. So mainly here, these soft acids are in combination with their soft bases, okay. Whereas when you're talking about, again, borderline acids, it can be like Fe2 plus, or we can say nickel 2 plus or zinc 2 plus, which are borderline in nature. They can again occur both as their sulfides as well as in the form of their oxides or carbonates, mainly because of their intermediate nature. So they can occur either as oxides, carbonates, or in combination with sulfide, right? So they can combine with either hard bases or with the soft bases. Next, talking about catalytic poisoning. So we know that the catalyst, it can get poisoned with the conversion of metal into its complex. So because of that, the catalytic poisoning can take place. So all the soft bases which can complex with metals in atomic state will act as poison towards the metal catalyst. So for example, when I'm talking about the metal atoms with the oxidation state 0, okay, the metal atoms I'm talking about, not the ions. So they are soft acids, right? They act as soft acids because obviously they have no charge. So because of which they act as soft acids. Now you can take the metal catalysts which are under this category. I can give examples: nickel, platinum, or it can be cadmium. You can also use molybdenum, chromium, all this without the charge, right? So these are the metal catalysts. Now, these can be poisoned by certain substances like carbon monoxide, or it can be the unsaturated hydrocarbons, like it can be like alkenes, alkynes, or dienes, even the arenes, okay? Along with that, R3P, right? Tri-alkyl phosphine. So all these can be used to poison these particular metal catalysts, mainly because of the soft interaction. So these are also soft in nature, right? They are soft bases. Now, this soft bases and these soft acid can combine together. So soft interaction can take place, because of which the metal catalysts, which are soft acids, can be poisoned by these particular soft bases. So if you're so now what happens if hard bases are present? So let us say if there are hard bases which contain the nitrogen or oxygen or fluorine as the donor atoms, then such bases they cannot poison these particular metal catalysts, mainly because of the hard soft interactions, the formation of the complex between the metal as well as these particular hard bases cannot take place, because of which the catalytic poisoning does not occur in the presence of hard bases. Next, talking about the limitations of HSAB principle. So mainly the hard and soft factors, according to this HSAB principle, they are independent of the acidic or the basic strength. It is not going to explain us about, based on these interactions, which acid is stronger, which one is a weaker acid, why certain bases have the higher basicity when compared to the other bases. All these are not explained according to the HSAB principle. But sometimes even this rule, when I'm talking about the limitation, so it is violated by the acid or the base strengths, which can lead to more stable hard soft systems also. So because of which we say that overall, although this HSAB principle is successful in explaining many other factors, and also there are many applications with respect to this HSAB principle, but still it cannot explain certain different reactions where hard soft systems also can be stable enough. So suppose we take an example now. So SO3 2 minus, which is a soft base. Now suppose if it reacts with HF, which is nothing but the hard acid. So it should give HSO3 minus, along with that F minus. So here this is hard, whereas this is hard soft, right? So according to the HSAB principle, this particular reaction should not be feasible. But when this reaction, or when you're talking about this particular reaction, this reaction can occur. Okay, so these are a few limitations with respect to the HSAB principle. Now coming on to the relative strength of acids, and what are the various factors we need to keep in mind when we are talking about the strengths of acids. Now, when you're talking about the strengths of the protonic acids like HCl, HNO3, sulfuric acid, HCl, HF, all these, they can be compared by their tendency to give the protons, because all of them, they have protons, right? So again, the strength depends upon various factors like nature, structure, as well as the periodic position of the compound. So how the atoms along with the H plus, so which are the other atoms that are present. So based on that, based on the position of these atoms, we can decide the relative strength of the various acids. Now, we know that when you're considering these acids like HCl, the nitric acid, it can be sulfuric acid. So all these are considered as strong acids without any doubt, right? Similarly, we have this acetic acid, CH3COOH, or we can have HF, or it can be HCN. So all these are considered as weak acids, right? So mainly when we are talking about these acids, the ionization of the acid in water, it measures the relative strength of any acid. So let us look into the ionization of a particular acid. Let us take it as HA. So this HA can ionize into H plus and A minus, right? So if I'm taking the initial concentration, so let us take the initial concentration of Ha as C. So initially, both of these ions will not be present. So let us take it as 0. Now, later what happens is after the dissociation, after certain time, we have this concentration of Ha, C minus alpha C. So here let alpha C of both of these ions will be formed. So I can write the initial concentration was C. So C minus alpha C. That is at equilibrium. So this is the initial concentration and the equilibrium concentration. Now, using this, we can write the equilibrium constant for this particular reaction. So Ka is nothing but concentration of H plus into concentration of A minus divided by concentration of Ha, the undissociated acid, which is in the denominator. Now, H plus concentration is alpha C into A minus concentration is again alpha C. Here we have in the denominator, we have C minus alpha C. So I can also write it as alpha square C square. Now C, I can take it as common. So 1 minus alpha, right? So this 1C and 1C, I can cancel out each other. So alpha square C divided by 1 minus alpha, right? Now in the denominator, we know that alpha is much lesser than that of 1. So I can also consider 1 minus alpha as approximately equal to 1. Here, Ka is nothing but the dissociation constant or the ionization constant of the acid, and mainly it can help in measuring the relative strength of an acid. Now, if the acid is stronger, then the value of Ka will be higher. Okay, so Ka value is higher, which shows that the acid is more stronger. Right. So now you can also calculate the pH. So pH of the solution is given as pH is equal to minus log of concentration of H plus, or I can also write it as minus log of alpha C, right? So alpha C is nothing but the concentration of H plus, which we have written here. So now we can also write the pKa value. So pKa is nothing but minus log of Ka, which is nothing but 1 by log of Ka. Right. So from this, it is very clear, higher the value of pKa, the weaker is that particular acid. Now talking about the classification of acids. So again, the acidity of the acid, it depends upon the nature of the compound, again, the structure or the position, as we've already discussed, the position in the periodic table. So if you're talking about the classification under hydro acids, we have HCl, we have H2S, PH3. So these are a few examples. Under oxo acids, we have examples like HClO4, then we have H3PO4. Okay, these are a few examples. Again, solvated cations can also act as acids. For example, like NH4 plus or AlH2O6, this complex with a 3 plus charge. So these are a few examples. Next, coming on to the factors which affect the strength of the hydro acids. So first one is the effect of electronegativity. So when you're talking about the hydro acid strength, so there is a general increase in the strength when you're going from left to right along a period. Okay. So for example, if you take the hydrides of carbon, so CH4, then we have NH3. After NH3, we have oxygen. After N, so hydride of oxygen is water. Then hydride of fluorine, we have HF. Right. So when you're talking about the acid strength, so HF is more stronger than water, and then NH3, and then we have the CH4 with the least acidic strength. So this trend can be explained on the basis of the increase in the electronegativity as we move from carbon to fluorine, right? This is with respect to the electronegativity. And this particular trend, whatever you can see, that is the acidic strength, right? So now it is very clear with the increase in the electronegativity of the central atom, the tendency to pull the electron pair from the hydrogen, it increases, and because of which the dissociation of the hydrogen becomes more and more easier, right? We know that fluorine is more electronegative when compared to that of oxygen or nitrogen as well as carbon. So it pulls the electrons towards itself. So because of which the removal of H plus becomes more easy, because of which the acidic strength of HF is higher when you're comparing it with the other compounds, whichever you have taken, that is water, ammonia, or the methane. Right. Now, this particular trend based on the electronegativity, it is only valid with respect to the period. Okay, but it does not hold good as we move down a group. Now, again, although there is difference with respect to the electronegativity, in terms of the trend down a group, it is a bit different. Okay, so acidity in a group increases with a decrease in electronegativity as we move down the group. So, for example, let us take the hydroacids of the group 7. Okay, so we have HF, then we have HCl, HBr, HI. So when I'm talking about the acidic strength, so HI will be highly acidic, then we have HBr, then HCl, and HF will be the least. So this is with respect to the acidic strength. Okay. So now, again, when I'm talking about the group 6, again, the acidic strength increases as we move down the group with water as the weakest acid. And again, if you're taking the hydride of tellurium, then that is the strongest acid in spite of water, which is the most polar on the basis of electronegativity. So if I'm going to take the group 6 or group 16, if I'm talking about in specific, then we have H2O, H2S, then we have H2Se, and then we have the H2TE, right? So this is with respect to the, again, acidic strength. Now, again, from this, it is very clear that the electronegativity difference is not the only factor which decides the acidic strength. Let us talk about one more factor which affect the acidic strength, which is nothing but the effect of size of the central atom. Now, besides the electronegativity, we have another factor which affects the acidity or the acidic strength quantitatively, right? So then this is nothing but the size of the central atom. Now, as we move down the group, the electronegativity, it decreases, right? We already know that. But we know that the size increases. So when you're comparing now electronegativity as well as the size, there is a competition between these two, right? We know that there is a decrease in this factor, electronegativity factor, but there is increase in the atomic size. Now, there will be a particular competition between which effect is higher. Now, we have to keep it in mind that the effect of increase in size, it appears to be more pronounced when compared to that of the decrease in electronegativity of the central atom. So because of which, with the decrease in electronegativity, the dissociation of the hydrogen, it decreases, the acidic character decreases, as we have studied in the previous first factor about electronegativity. But this is compensated by the increase in the size. So because of which it increases the overall acidic strength of that particular compound. Okay. So now let us take a simple example to make it more clear. Now if I take FCl BRI, okay. So we know that fluorine is more electronegative. So electronegativity, if I'm writing electronegativity, so we have fluorine 4.0. For chlorine, it is 3.0. Bromine is 2.8 and iodine is 2.5. So we know that electronegativity decreases down the group. But still, the acidic strength goes on increasing. Why it is increasing? Mainly because of the size. So the atomic size in case of, here I'm going to write it in terms of angstrom. So here it is 0.64, here 0.99, here 1.14, 1.33. So it is very clear that the iodine has a largest atomic size when compared to these fluorine, chlorine, as well as bromine. So because of the pronounced effect of the atomic size increase, there is increase in the acidic character of the respective compounds. Right. Next, coming on to the enthalpy of ionization. So mainly the acidic strength of the hydroacids, it depends on, we know that it depends on electronegativity as well as the atomic size. Now, the factors which influence the degree of electrolytic dissociation of the hydroacids in the aqueous solution can be explained by making use of this Born-Fajan-Haber cycle. Okay, so now suppose if I'm talking about the acidic strength of the acid HX, so it can be written as here, it forms H plus aqueous as well as X minus aqueous. So delta H, right? This is the change in the enthalpy. So let us look into how this delta H, the value of delta H can be found out by making use of the various factors. So here, Hx, delta H, which is the enthalpy of the reaction. So we have aqueous, here X minus aqueous. So here I can also write this as Hx. Now here Hx is in the aqueous state, right? So this Hx can be converted to the gaseous state, right? So this is nothing but delta H, that is dehydration. Next, this Hx on dissociation, right? It can give rise to hydrogen as well as halogen atoms, right? That is a dissociation. The second step is whatever here, if I'm writing this as a second step, this is the first step, right? So first step is dehydration, second step will be dissociation. Next, here H has to be converted to H plus. So that is nothing but the ionization. So H plus in the gaseous state. Now this will be converted to H plus in the aqueous state. So here we have delta H, and here we have again the ionization, right? So here again, X has to be converted to X minus, which is nothing but, again, this is in the gaseous state, right? And again, here we have this E, which is nothing but the electron affinity. And now this X minus in the gaseous state should be converted to the X minus in the aqueous state. So this is how, this is nothing but delta H. So this is for X minus, this is for H plus, right? H plus, right? So now let us look into each of these one by one. So first one, we know that it is the enthalpy of dehydration of this particular molecule, Hx, and it is getting converted to the gaseous state, Hx in the gaseous state. Now this particular enthalpy, the delta H value is positive, or in other words, energy is absorbed. Now second one is the dissociation energy, whichever I have written here. I've marked it as second one, second step. So here, mainly the breaking of the molecule Hx, that is in the gaseous state of this, into its gaseous atoms, that is hydrogen H as well as X, that is in the gaseous state. Again, this is also positive. Next is I. Okay, third one, we are talking about I, which is nothing but the ionization energy of the hydrogen atom, where one of the electron is removed out from the gaseous atom to give you H plus in the gaseous state. So now here we know that energy has to be supplied to remove the outermost electron. So because of which we know that energy has to be given. So that's why it is again positive. Okay, so this also is, and since energy is required, it is positive. Next, talking about the fourth, we write it this one as fourth. So this is nothing but the electron affinity of the halogen atom. So it is negative because energy is released when one of the electron is added to the halogen atom to make it a stable X minus halide ion. Right. Next, talking about the enthalpy of hydration of the X minus ion. So let me mark it as sixth one here. So this is the enthalpy of hydration, where the H plus in the gaseous state converts into the H plus in the aqueous state. So this is also negative because energy is released, right? Even when I'm talking about the enthalpy of hydration here, that is the last step, which I'm going to mark it as 7. So here, this is for the X minus ion. So here also, this particular energy is released here. So delta H has a negative value here. So the value of delta H can be calculated as delta H is equal to delta H of dehydration, right? Plus, I can add this dissociation energy, which is positive. Then ionization energy is also positive. Then obviously we are going to add this electron affinity, and then which is negative, this is negative. Next, delta H, that is hydration of H plus, which is negative. And also we have delta H, the hydration energy or the hydration enthalpy of X minus, which is again negative. Now, the endothermic changes are mainly here, whatever we can see, the 1, 2, and 3. These steps are the endothermic changes, which are positive, and the exothermic changes are all of these 4. Here, fifth one. So this will be fifth, and this is the sixth one. So all of these are negative, right? Mainly, we know that the value of delta H, it only gives us a tentative idea about the relative acidities of the halogen acids. Larger is the negative values of delta H, the greater is the acidity. Okay, so overall, we need to look into the negative delta H. So more negative it is, then more is the acidity of that particular halo acid. Okay, yes. So mainly, again, when we are talking about the complete analysis of the delta H, then we need to know about delta S also, which is again more of thermodynamic concept. So we are not going to discuss much about how to find out this particular delta H with respect to delta S. But for now, we can understand it with respect to the Born-Fajan-Haber cycle, where we can decide about which one is more stronger acid when compared to the other based on the overall delta H value. Right. So when I'm talking about HF, it is weaker when compared to that of the other halogen acids, mainly because it has high heat of dehydration as well as the high bond dissociation energy. So coming on to the next factor, that is basic strength of conjugate base. So the relative acid strength of the halo acids, it depends upon the basic strength of their conjugate base. So we know that for the halo acids, these are the conjugate bases that are present. That is for HF, we have F minus, for HCl, we have Cl minus, for HBr, the conjugate base is Br minus, and again I minus for Hi. So when we consider from F minus to I minus, we know that the size of the ion goes on increasing. And because of this, we know that the electron density goes on decreasing. So because of all of these factors, we know that as the electron density decreases, the tendency to attract the proton goes on becoming less and less, right? So it becomes less with the consequence basic character, which is going to decrease from the F minus to I minus. So based on this basic character, we can write it as the order F minus, Cn minus, Br minus, and I minus, mainly because of the change in the ionic size, which is increasing from F minus to I minus, and the density, electron density goes on decreasing, because of which this is the basic strength that is observed. Now, stronger the conjugate base, weaker is the acid. We already know that. So this is what we have studied till now. So when you're talking about the acidic strength, we can easily write that it will be HF, which is less acidic when compared to Cl, HCl, which is less acidic when compared to HBr, and Hi is the most acidic. We can also explain the acidity of group 6 hydrates in the same way. So we can write it as H2O will be less acidic when compared to H2S, which is again less acidic when compared to H2Se, and it is less acidic when compared to H2Te. Right. So next, coming on to the bond dissociation energy. So the relative strengths of these hydroacids can also be explained in terms of this bond dissociation energy. So bond dissociation energy, when you're talking about, now again, when I'm comparing this HF and Hi, so the bond dissociation energy decreases because it is easy to break the bond between hydrogen and iodine. Obviously, we know that iodine is larger in size, so the bond can be easily broken, right? So when you compare HF and Hi, here the bond dissociation energy is very less for Hi when compared to that of HF. Or when you're comparing water as well as H2TE, again we know that for H2TE, the bond dissociation energy is less, but for water it is more. So based on this, we can easily say that since here the bond dissociation energy is less, so it is easy to break the bond, and obviously the H plus can be formed very easily, because of which it is highly acidic. So based on bond dissociation energy also, we can easily explain the acidity of these various halo acids. So we can say that when you compare HF, HCl, HBr, as well as Hi, if I'm talking about the bond dissociation energy, so here in terms of course, kilojoules per mole. So for HF, it is 568. For HCl, it is lesser, that is 431 kilojoules per mole. For HBr, it is 366. And for Hi, it is still less, that is 298 kilojoules per mole. So based on this also, we can easily explain the acidic nature of these various halo acids. So let us now move into the factors affecting the strength of oxo acids. So let us look into the factors one by one. So first, coming on to the electronegativity as well as the size of the central atom. Now let us consider an oxo acid. Let me write it as EOH, right? So when you're considering the nature of this E, if this E is small as well as highly electronegative atom, then it attracts the shared electron pair more strongly. So because of this, what happens? The polarity of this particular OH bond increases because the E, which is the atom which is attached to the OH group. So what happens? This is again, it is attracting the shared pair of electrons towards itself. So because of the polarity increase in the OH, so the removal of H plus becomes more and more easier, right? So because of that, the acidic strength increases. So this is what happens with respect to the electronegativity as well as the size of the atom. Mainly here we are considering it as the central atom, which is directly attached to the OH, so that the polarity is changed and the removal of H plus becomes more and more easier. So now, again, when I'm talking, I can generalize it as higher the electronegativity of E, more easily the proton is lost, as well as more is the acidity of that particular oxo acid. Now, let us talk about in a particular group what happens. As we move down a group, we know that electronegativity decreases and the size increases, and obviously the acidic character will go on decreasing. Okay, so now let me just give a simple example. So the acidic character of oxo acids of halogens, let us consider it. So if I take HClO, HBRO, and HIO. So we know that again, as we move down the group, the electronegativity of the other atoms. So here we are talking about the halogen. So E here is the halogen. So the electronegativity decreases as we go from chlorine to iodine, right? Because there is increase in the size of the atom. So now if the electronegativity is less, the polarity of the OH bond becomes lesser. So removal of hydrogen will become difficult, right? So because of that, the order here is HClO will be highly acidic when compared to HBRO, which is again more acidic when compared to that of HIO. So this is also confirmed by the pKa values. So here it is 7.4. For HBRO, it is 8.7. And for HIO, it is 11.0. So we know that higher is the value of pKa, less acidic is that particular compound. Right. So again, when I'm talking about this EOH, it behaves as an acid only if E has electronegativity value greater than 1.8. So only if this E has the electronegativity value according to the Pauling scale, if it is more than 1.8, then only that particular acid will be considered as a strong acid, and this E, the electronegative effect of this E will be predominant. Okay. So now suppose if I'm talking about, let us say ClOH. So we know that chlorine, it has the high electronegativity, that is 3.0 is the electronegativity of chlorine. So this behaves as an acid. Now, let me talk about LiOH, right? So it is a base. Why it is acting as a base? Because the electronegativity of lithium is 1.0, which is lesser than 1.8, right? So because of which this LiOH cannot act as an acid. So next, coming on to the second factor which affects the strength of the oxo acids. So now let us talk about presence of additional groups. So along with, let us say about E. So along with that, if there is certain additional groups that are attached. So R, let us consider it as R. So R can be any additional group that has been added. So it can be the extra oxygen that is present, right? So whenever these additional groups are present, then the relative acidity increases with the increase in the oxygen number. So now if this R is taken as oxygen, let us say, so if the number of oxygen atoms increases, so if I'm going to take these additional groups as oxygen, so if the number of oxygen atoms increases in the molecule, then the acidic character is also going to increase, right? So let us look into the series of the oxo acids of chlorine. Now, let us take it as HClO with one oxygen. Next, again, I'm taking HClO2 with two oxygen atoms. Now here HClO3, and let me consider HClO4. So it is very clear that if the number of oxygen atoms are more, then obviously the acidity is also more. The acidic character of that particular compound is more. So I can give the this order as follows, right? So now here we know that when I'm considering the oxidation number, right, of chlorine. So let us calculate here. So here it is +1. So let us take it as X here. It is -2. So X minus 1 is equal to 0. So oxidation state of chlorine here is +1. Here H is +1, right? For chlorine, I'll take it as X. Here it is -4 because two oxygen atoms are present. So X minus 3 is equal to 0. So here it is in the +3 state. Now here again, if I'm taking +1 for chlorine X, here it is -6. So X minus 5 is equal to 0. So here it will be plus. So here +1 X minus 8. So X minus 7 is equal to 0. So here it is in the +7 state. Now, this is with respect to the oxidation number of chlorine, right? So same way, if I'm taking the pK values, we can observe that here it is 7.52, here 1.94, here it is -3, and here it is -10. So it is very clear that lower the value of pK, stronger is the acid. So it is, you can see that in HClO4, the pK is very low. So because of which we can say it is a very strong acid, right? Next, talking about the stability of the conjugate base. So Here we are again comparing the same molecules, whatever we have discussed in the previous factor. So here, these are the conjugate bases which are formed by the removal of the H plus ions. Now, the stability increases due to the charge delocalization over the pi bonded oxygen atoms. So we know that again, the conjugate base is formed because of the removal of H plus, and these are formed by the removal of loss of proton, and this is stabilized by the charge distribution mainly. Okay, so now this charge stabilization, it is minimum in ClO minus, whereas it is maximum in case of ClO4 minus. So what does it indicate? It indicates that ClO minus will have the minimum stability, and because of which there is maximum attraction towards H plus. So if there is maximum attraction towards H plus, so it is very difficult to remove this H plus off, right? So because of which this particular acid is acting as a weak acid, right? Which is nothing but HClO. Right. So in this case, when I'm talking about ClO4 minus, it has the greatest stability because of whatever I told about the distribution of the charge by the pi bonded oxygen atoms. So delocalization over takes place. So because of that, because of charge delocalization, so this ClO4 minus, it has the greatest stability, and obviously it will have the weakest attraction for H plus. So if the attraction towards H plus is very less, you can easily remove off the H plus. The proton can be easily removed off, making it the strongest acid. That is, HClO4 will be a strongest acid. So let us look into how this delocalization takes place. So in the first case, so OCl. So here you can see there is a double bond character. So this will be minus. So delocalization takes place in this way. So in this case, so there are two oxygen atoms, right? So here the delocalization takes place with the two oxygen atoms, right? So next, so again here it is -1 because one proton has been removed. So in case of where there are three oxygen atoms, again the delocalization takes place in this way. Okay, so it is again minus charge. Now if there are four oxygen atoms, so there is delocalization throughout. So this is how it takes place. And here, this is how the stability increases. So in this case, this is the most stable because of greater delocalization, and here it is the least stable. Right. So next, coming on to the inductive effect. So inductive effect, it is significant in case of the carboxylic acids. So when you're talking about the acetic acid, we know that it is a weak acid. Now, if the methyl hydrogen in the acetic acid is replaced by an electronegative atom like chlorine, then the acidity is drastically increased. Right. So more electronegative atoms should be substituted with that of the hydrogen. So then what happens? The acidic character goes on increasing. So as the number of electronegative substituents increases, then it increases the overall acidity of that particular compound. So now, if I'm considering acetic acid, then now if I'm replacing one of the hydrogen with chlorine, so I get here Cl, CH2, COOH. Now, if I'm replacing two hydrogens with two chlorine atoms, then I'm going to get here Cl2, CH, COOH. Now, if all the three hydrogens are replaced, then we have Cl3, C, COOH. Right. So now, here, if we are considering the pKa, here it is 4.8. So here it is found to be 2.9, here 1.3, and here it is 0.7, which clearly shows that this is highly acidic, where three hydrogens in the methyl group is replaced by the chlorine atoms. So because of which, because of the highly electronegative nature, so then this trichloroacetic acid acts as a very strong acid. Now, what happens is we know that these electronegative substituents, they pull the electrons towards themselves. So because of which this hydrogen can be easily removed as a proton because the electrons are pulled towards the electronegative atom. So the H plus removal will be more and more easier, right? Now, next talking about the polybasic acids. So here, in a particular polybasic acid, we know that there are successive pKa values that need to be considered. So it can be pKa1, pKa2, pKa3. So these values will be usually in the ratio of 1:4:8. So we can take a few examples. So suppose we take H3PO4. So if I take pKa1, pKa2, as well as pKa3, so for H3PO4, it will be in the ratio, so 2.1, here it is 7.2 and 12.0. So approximately it is in this given ratio of 1:4:8. Similarly, I can also take H3AsO4. So here it is 2.3, 7.0 and 13.0. Right. So again, you can see the general ratio between the values of pKa1, pKa2 and pKa3 will be in the ratio of 1:4:8. Now again, pKa, it depends on the formal charge of the central atom and also the number of non-hydroxyl oxygen atoms. So this is again the pK, the particular formula is given by this relation, that is 8.0 minus 9.0 into m plus 4.0 into n. So where we have this m is nothing but the formal charge on the central atom. Then when we are talking about the n, it is nothing but the number of non-hydroxyl oxygen atoms that are present in the acid. Okay. So now how do we calculate the formal charge? It is very simple. We have the number of valence electrons that are present in the central atom minus half into the shared electrons that are present minus unshared valence electrons. Now first, let us look into how the pK values change with respect to the m, the value of m that is present here. Now, if I'm taking the general formula, in this case, OM, E, OH, N. Okay, now here I'm not considering the formal charge. Now here m is nothing but the number of oxygen atoms. Now, based on that, if m is equal to 0, then the pK values will be greater than or equal to 7, which indicates they are weak acids. Okay, very weak acids. So here we have the example BOH thrice. Suppose we have m is equal to 1. I hope it is clear. Now, what is m that I'm talking about? We are talking about OM, E, OH, N. So, in this particular equation, I'm talking about the value of m. So, m is equal to 1. Then, in such case, the pK is almost equal to 2. So, which indicates they are weak acids. So, for example, we have OCl, OH. Okay. So, we know that as the number of oxygen atoms increases, or in this general formula, as the value of m increases, then the acidic strength becomes more, right? So then we have m is equal to 2, then the pK value will be almost equal to -3, which indicates that these acids are strong acids. So for example, we have O2, Cl, OH, right? Similarly, if I have m is equal to 3, then the pKa value will be almost equal to -8. So we have very strong acids, right? So I can give the example O3ClOH, right? And we already know that as the number of oxygen atoms in these oxo acids, as it increases, we know that that particular compound becomes more and more acidic in nature. Now talking about the calculation of the formal charge. So let us look into the calculation of the formal charge of the various compounds. So first let us only calculate where it is ClOH. So we know that chlorine, it has 6 electrons like this, 3 lone pairs of electrons. Now, how do you calculate the formal charge? So this is with respect to the formal charge, right? So here we know that chlorine is a halogen atom. So valence electrons will be 7 minus half into shared electrons are 2, right? It is forming only one bond. Then minus unshared valence electrons. So we know that there are 3 lone pairs, so totally 6 electrons. So 6, 7 minus 1 is 6, minus 6 will be 0, right? So next, talking about here when one oxygen is introduced. So we have again OH. Now the number of lone pairs of electrons are reduced, right? So again, the valence electrons remain the same. Now here half into number of shared pair of electrons will be 4 because it is forming 2 bonds, right? And the number of unshared electrons are 4 here. So 7 minus, here it is 2. 7 minus 2 is 5. 5 minus 4 is plus 1, right? So next, let us take one more example. So Cl, here we have 2 oxygen atoms that are attached and OH. So here again I have, right? So here there is only one lone pair of electron, sorry, because it is already forming 3 bonds. So here 7 minus half into. Now how many bonds are formed? There are 3 bonds. So obviously 6 electrons are shared and there is only one unshared pair of electrons. So 7 minus 3 is 4. 4 minus 2 is 2. Right. Next, talking about where 3 oxygen atoms are present. So Cl, here 3 oxygen atoms. Then here we have the OH. Right. Again, it is 7 minus half into. So there are 4 bonds that are formed. So 8, right? Minus, here there is no lone pair of electron on chlorine or the unshared electron pair. So 0. So 2 and 4. So 7 minus 4 is 3. right? So it is very clear with respect to the formal charge. Also, we can easily find out the acidic strength of that particular molecule, right? So now let us look into the related examples. So let us take HClO4, right? Where M is equal to +3, which is a formal charge, right? And then, so we know that we are going to calculate it with this particular formula, that is pKa is equal to 8.0 minus 9.0 M plus 4.0 N. So let us calculate the pKa for this particular molecule. Now for HClO4, just we calculate the formal charge, right? It is +3. So I'm going to substitute this M is equal to +3. Now we also have N. N value is nothing but number of non-hydroxyl oxygen atoms. So it is very clear in the structure. There are 3 such oxygen atoms. So N is equal to 3. Right. So now let us substitute this in the formula. So pKa is equal to 8.0 minus 9.0 into 3 plus 4.0 into 3. Right. So we can find it out. We can, when we do the calculation. So 8 minus 9 into 3 is 27 plus 4 into 3 is 12, which gives you the value -7, right? So now, next, let us calculate for HClO3. So M for HClO3, that is the formal charge. So HClO3, this is the one, right? So formal charge is +2. So let us calculate. Next, N is equal to that, which is nothing but the number of non-hydroxyl oxygen. So we have 2 here. So N is equal to 2, right? Now let us substitute it in the formula to find out the pK values. So pK is equal to 8.0 minus 9.0 into M, right? M is 2 here. Again, 4.0 into 2, which is N. So here we have 8 minus 9 into 2 is 18 plus 4 into 2 is 8. Right. So when we do the calculations, we can see that it is -2. So this is with respect to the HClO3. From this, it is very clear that HClO4, which has a lower pK value, is a stronger acid, and HClO3, it has -2, which is a bit higher value when compared to that of the pK value for HClO4. So we can easily interpret that HClO4 is a stronger acid than HClO3. Next, coming on to the factors affecting acidic strength of hydrated cations. So small and highly charged cations, they have a large charge to size ratio. So because of which they promote the rupture of the OH bond when you're talking about the hydrated cation. So mainly this hydrolyzed species and H3O plus ions are formed in this particular reaction. So because of which, based on this, we can decide the acidic strength of the hydrated cations. So let us look into the equation. So we have M H2O N. So let us take M plus as the charge that is present on this hydrated cation. So this in the presence of water. So you're going to get M H2O N minus 1 OH. Here the charge will be now M minus 1 plus charge. Along with that, there is H3O plus that is produced. So more is the charge to size ratio, then the OH bond polarization will increase. So if the OH bond polarization takes place, then as we have already studied, the removal of the proton becomes more and more easier, because of which the acidity goes on increasing. So next, coming on to the relative strength of bases. Higher is the Kb value, like how we have studied about acids. More is the Ka value, stronger is the acid. So similarly, higher is the Kb value. It indicates that the base is a strong base. When you're talking about pKb, like how we spoke about pKa, so if the pKb value is higher, then it indicates that the particular base is weak. So let us consider the ionization of a base. So let me take it as BOH. So this on ionization will give you B plus OH minus. Now the equilibrium constant for this particular reaction, I can write it as Kb. Here, concentration of B plus into concentration of OH minus divided by concentration of BOH, where Kb is nothing but the ionization or the dissociation constant of the base. So it measures again the relative strength of the various bases. So based on this Kb, we know that if it is higher, we know that it is a stronger base. And we also know that pKb is equal to minus log of Kb. This is similar to whatever we have studied in terms of acids. So which is nothing but minus log of Kb. So more is the value of pKb, lower is the strength of that particular base. Right. So next, coming on to the basicity in amines. We know that ammonia is a weak base in aqueous medium, whereas when you're talking about substitutions, okay, so methylamine, where methyl group is substituted in place of one of the hydrogen. Now, this methylamine is stronger when compared to ammonia. Now, suppose if you're considering NF3, it is not at all basic. Now, let us consider this basic strength, how it varies. So, ammonia. So, now, suppose if I'm talking about the substitution by the electron releasing groups, such as the CH3 group. So, we are getting CH3NH2. Then suppose if both of the hydrogens are replaced, then again we have NH, here CH3, CH2, which is more basic. So as I already told, when the electron releasing groups are added as substituents to the amines, to the ammonia especially, so what is going to happen is these electron releasing groups increase the electron density on nitrogen, because of which the lone pair of electrons that are present on the nitrogen is more available. Because of these reasons, we say that the basic character goes on increase, right? So now, suppose if the electron withdrawing group is substituted to the ammonia, what is going to happen? So let us say we have ammonia. Now, one of the hydrogen is replaced by NH2 group, okay? So where there is electronegative nitrogen atom in the substituent, suppose I replace one of the hydrogen with OH group. Again, oxygen is an electronegative atom. Now, if all the hydrogens are replaced by fluorine, which is highly electronegative, then we have the basic strength in this order. So whenever an electron withdrawing group or the electronegative substituent is added as a substituent to ammonia, then what happens? The basic strength goes on decreasing, because now the electron withdrawing group, it pulls the electrons towards itself, because of which the lone pair of electrons on nitrogen is not easily available. So because of that particular reason, now the basicity decreases in such substituents, where in such molecules where the substituents have electronegative atoms. Now, talking about the reason for the basicity of the amines. Now, whenever the replacement of hydrogen in the NH3 takes place with the different electronegative groups like NH2OHF, so I've already shown the order, right? So we know that the basicity decreases because these groups, they withdraw the electron density from the nitrogen atom, and because of which the overall basicity is reduced, right? So now we know that here NH2. Now to this, if I'm going to add OH, so here the electrons are withdrawn because of the oxygen. So now the electron density on this nitrogen decreases. So here the electron density decreases. So because of which the molecule, it cannot act as a very strong base. Next, talking about replacement of the hydrogen in ammonia by electron releasing groups. It can be like alkyl group. So this increases the electron density on the nitrogen atom, and again here there is increase in basicity. So we have CH3 here, NH2. So obviously these are electron releasing group that is added, CH3. So overall the electron density on the nitrogen increases, thus increasing the basic character. Basicity also increases with the increase in the number of alkyl groups. So I can write it as, now suppose we have nitrogen, here one hydrogen, two methyl groups. Now if I take again two hydrogens, but I am only taking one methyl group. So here there are two electron releasing groups which are present in the molecule. So here the basicity, obviously it increases because of the increase in electron density on the nitrogen atom, because of the electron releasing groups. But however, we need to remember one thing: the tertiary amines are weaker bases when compared to that of the primary amines. So let us look into the relation. Okay, so I'm going to write it here. So here R2NH, where R is a alkyl group, is an alkyl group. So it will have higher basicity when compared to the primary amine. And here the primary amine will have higher basicity when compared to that of the tertiary amines, but they will be more basic than ammonia. Right. Mainly now talking about the tertiary amines, why these are more, why these, although they have three electron releasing groups that are attached to nitrogen, but still it is less basic. The reason is that mainly there is increased steric effect because of the three alkyl groups on the small nitrogen atom, and lower energy of solvation is also present here in the tertiary amines when compared to the other amines. So because of all these reasons, the tertiary amines are less basic compared to that of the secondary or the primary amines. Next, talking about the basicity of the metal oxides. So overall, I can classify metal oxides into three types. That is the acidic oxides, basic oxides, and amphoteric oxides. So acidic oxides are the ones which increase the H plus concentration when it is dissolved in water. So for example, we have N2O5, the oxide of nitrogen. So when you dissolve it in water, so you're going to get 2H plus along with that nitrate ion, right? So here it is very evident that H plus ion concentration is increasing. So because of which we call this N2O5, this particular oxide, as acidic in nature. Next, talking about basic oxide. So these oxides, they decrease the H plus concentration when dissolved in water. So mainly the decrease in the H plus concentration is caused by the formation of OH minus ions. So OH minus ions can combine with the H plus to form water. So overall, there is decrease in the H plus concentration when dissolved in water, when these oxides are dissolved. So let us take the example of calcium oxide. So in the presence of water, you're going to get calcium ion along with that OH minus. So as I already told here, OH minus ions can combine with H plus to form water. So overall, there will be decrease in the H plus concentration. Next, coming on to the amphoteric oxides, they behave as both acids as well as bases. So let us look into aluminium oxide. So in the presence of acid, they can react with acid. So you're going to get Al3 plus and obviously water, because here aluminium oxide itself is acting as a base. So when it is reacting with acid, so it is like a neutralization reaction. So you're going to get aluminium, that is 3 plus aluminium ion along with that water. So here it is acting as a base. Same way. So let me balance the equation. Here 6, here I can write 2 and here 3. Right. So I can also write one more reaction of aluminium oxide where it is acting as an acid. So Al2O3, it can react with base OH minus. So here you're going to get AlO2 minus along with that water, right? So here it is acting as an acid. So let us balance the equation. Here 2, here also 2. Yes. So this is how we are going to look into the various types of metal oxides, and based on that we have different types: acidic, basic, as well as amphoteric, based on the reactions. Now, talking about how the basic character changes. So it increases with the increase in the atomic weight along a particular group in the periodic table. So as you move down the group, we know that atomic weight increases. So because of which the basic character goes on increasing. So let us look into the group 13 oxides. So we have B2O3, then aluminium oxide, then we have gallium oxide. Next we have indium oxide. And so here, when I'm considering the nature, this is acidic in nature. Now, if I'm considering these two, these are amphoteric. And these two, the last two, if I'm considering, these are basic in nature. Okay, so you can easily see that as you move down the group, the atomic weight goes on increasing because all of these are belonging to the same group, the group 13, right? Now, the first one is acidic. Now, as you move downwards, we can see that slowly the basic character starts appearing because aluminium oxide, it can act both as acid as well as base. Now, when you go down the group, it is more basic. So it is very clear that the basic character of these oxides goes on increasing as you move down the group. Next, talking about the charge on the metal, when it remains the same, the atomic size, obviously it is going on increasing down the group. So because of which the charge to size ratio decreases. So we know that basicity increases with the decreasing charge to size ratio. So this is the main reason why you're looking into how the basic character, it goes on increasing as you move down the group. We can also take the consideration of group 2 oxides. Group 2 oxides. So we have oxide of beryllium, then we have magnesium oxide, calcium oxide, we have strontium oxide, as well as barium oxide. Now, all these are group 2 oxides. Now, if I'm considering the first one will be amphoteric. Next, we have magnesium, which is weakly basic. Next, if I'm considering all of these, the basicity increases down the group. All of these are basic, and obviously the basicity, it increases. Basic nature increases down the group. Now, why this? First of all, I told you about the charge to size ratio. So since it decreases, the basicity goes on increasing. Now, when I'm talking about this particular oxide, which is acidic in nature. Now, mainly here, the boron, we know that it is in the +3 state, right? This is having a high polarizing power. So mainly because of this, the charge to size ratio is exceptionally large relative to the other oxides that are present in the same group. So because of this, this particular B2O3, the oxide of boron, so it polarizes the oxide ion because of the small size as well as the large charge, that is 3 plus charge that is present on boron. So because of this, it is acidic in nature. Right. Similarly, even this, it shows a different character when compared to the other oxides of the same group. So here, again, Be, it is in the +2 state here. Again, it has high charge to size ratio. So based on this, the basicity of BeO is significantly lower when compared to the basic nature of the other members in the same group. So this is mainly because of the small size as well as the larger charge that is present on these particular ions, that is Be2 plus as well as Be3 plus. So it causes the polarization of the oxide ion. So because of that, here we can say that the basic nature is less, or especially when I'm talking about B2O3, it is acidic in nature. First, coming on to the inductive effect. So we know that electron withdrawing substituent, it will make a Lewis acid stronger, whereas an electron releasing substituent will decrease the acid strength. So this we are already well aware about. So let us look into the example. So suppose we have CH3 thrice with 3 methyl substituents with boron. Then we have BH3 and then we have BF3. Here we have 3 electron releasing groups. So when electron releasing groups are present, we know that the acidic strength, it decreases, right? So here the acid strength is lesser compared to BH3. Now here there are electron withdrawing substituents which are present, which have been replaced. The hydrogens have been replaced with the fluoro, which is electron withdrawing group. So obviously here the acidic strength will be higher. So this is with respect to the inductive effect. Now talking about the next factor, that is resonance. So according to the inductive effect, now if I'm considering these 3 different halides, that is BBr3, next BCl3 and BF3, these different halides, it should be very clear that we know that this BF3 should be having larger acidity compared to BCl3 as well as BBr3. But it is found that this particular order is wrong. Now, the observed acidity is in this order. BBr3 is having higher acidity when compared to BCl3 and BF3 is having the lowest acidity. So it is very clear that based on only inductive effect, we cannot explain the acidic strength of these boron halides. So how can we explain this? We can explain this in terms of resonance. Now, mainly in case of these boron halides, first of all, we should remember that the halogen atoms, they have a tendency to contribute electron density towards the boron atom. Now, this is called as the back donation. Now, back donation is mainly, it is the strongest in BF3 because fluorine and the boron, in both of the cases, it is mainly because of the 2p orbital overlap, so which results in the back donation. Whereas in case of BBr3, so let us look into how it takes place. So first of all, in BF3, it is more effective, as I told, 2p and 2p. But we know that in case of bromine, it is a 4p orbital which is involved. So 4p and 2p overlapping is not so effective. So because of that, back donation is not effective in case of BBr3, but it is very highly effective in BF3. So because of the back donation, the acidic character of this BF3 is the least when compared to BCl3 as well as BBr3. So let us look into how this takes place, how this back donation takes place. So let us say boron, it has atomic number 5. So we know that it is 1s2, 2s2, 2p1, right? Similarly, I can also write it as for fluorine, atomic number is 9. So 1s2, 2s2, so 4 are done. So 5, 2p5, right? So now in case of fluorine, we have the filled orbitals of fluorine, especially here 2s2, and here only there are already 5 electrons. So 6 electrons can be filled, of course, in 2p orbital, but there are 5 electrons. So now, because of this, and here it is seen that the 2p orbital, it has only 1 electron, and we can also write this as, suppose we have 3 orbitals like this. In 2p, we have 3 such orbitals, but only 1 electron is present in this 2p orbital in case of boron, right? So because of this, there will be the back donation. So if I take this fluorine, right? So this is the filled p orbital, right? Now, if I'm talking about the boron, so which has the vacant orbital, vacant p orbital of boron. So there can be back donation in this way, right? So obviously there is a bond here and there are different fluorine atoms which are present, right, in BF3. Now here, this is how the back donation takes place from the filled orbital of fluorine towards the vacant orbital of boron. So because of this back donation itself, we say that, so in BF3, it is highly effective, as I already told, because it is mainly because of the 2p orbital overlap. So here the back bond is formed. So this type of back bonding mainly results in the lower acidity of BF3, right? So I can also show it in this way. So so here two bonds are there. So here already there is one bond. Now because of back donation, you can see that here it is mainly because of back donation, I can put a partial positive charge on fluorine and here a negative charge. So this I can also write it as F, here B. Now this can also be written in this way. So plus and minus here, F. I can also write one more structure. So F, B, here F, here F, because of the back donation. So here plus and minus. So because of the back donation, I can write also the resonance hybrid of the structure. So F, here B, F and F. Now overall there is partial double bond character because of mainly because of the reason of back donation. So I can write it in this way. So now here the boron atom is no longer so electron deficient. So because of which the acidic character decreases, right? While in case of when I'm talking about the BBr3, here as I already told, there is poor 4p, 2p orbital overlap. So here the boron, it remains as electron deficient in case of BBr3. There is no effective back donation. So because of this, it is acting as a strong Lewis acid. So this explains why this particular order is observed with respect to the acidic strength. The next factor which affects the acid strength is mainly because of the steric effect of the substituents. So under this, we can easily classify the acids and bases based on the various strains. So let us look into the various examples, that is pyridine, 2-picoline as well as 4-picoline. So there is something called as the F strain or the front strain. So let us look into these different compounds. So this is pyridine. We can also write the structure of picoline, where we have a methyl substituent to the pyridine ring. So it is in the second position here. So this is 2-picoline. And we also have another example of picoline, where the substituent is in the fourth position. So we have 4-picoline. Right? So here it is very clear that nitrogen has a lone pair of electrons. So because of which we already know that even pyridine is basic in nature. So now when any of these is made to react with BCH3 thrice trimethyl borane, so what is going to happen? So in this reaction between the Lewis acid as well as the Lewis base, so here the pyridine as well as these picolines, they are acting as Lewis bases, whereas the Lewis acid that is taken is the trimethyl borane. Now the adduct bond energies in this case, so in case of pyridine, it is 71 kilojoules per mole, whatever the adduct is formed. Now in case of 2-picoline, it is 42 kilojoules per mole, whereas for this 4-picoline, it is 76 kilojoules per mole. Now you can see there is a difference in the energy of the adduct when the adduct formation is taking place in case of the 2-picoline. So in the basis, when you are talking about inductive effect of the methyl group, so 2-picoline should have been acted as a stronger donor, right? Because the CH3 is an electron releasing group. So based on this, we could say that the lone pair of electrons on the nitrogen that is present will be more available to be forming a bond with the acid, right? Because it increases the electron density on nitrogen. But you can see that it is something, the opposite effect is observed, right? This is mainly because of the steric hindrance that is occurring between the CH3 group of the 2-picoline as well as the CH3 group that is present on the boron. Okay, so let us look at the adduct that is formed between the 2-picoline and trimethyl borane. So here we have the methyl group in the second position, and this is forming a bond with boron, which is again having 3 methyl groups that are present attached to it, right? So CH3 and here one more CH3. So it is very clear that there is steric effect that is playing a role here. So because of which, in this case, whatever the bond energy, so you can see it is very less in case of 2-picoline. So this is how the acidic nature or the basic nature is defined. So here, because of the presence of the steric effect, you can see that the 2-picoline, it has a less basic character when compared to the other two compounds, right? So next coming on to, again, when I'm talking about this is nothing but, as I already told, it has a special name which is called as the F strain or the front strain. So it has, again, a very good, strong influence on the stability of the adduct that is formed because of the alkyl group. Mainly they operate in large volumes, and here also there is rotation, random rotation. So because of this, we can say that mainly this F strain influences the stability of both acids as well as bases. Next, talking about here, when I'm talking in detail about the steric effect, in that I'm going to speak about the B strain or the back strain. So inert substituents, when you're taking into consideration, they fold back behind the donor or the acceptor atom when the formation of complex takes place. So here in case of boron, it changes from the sp2 to the sp3 hybridization when it forms complex, right? So if I'm taking Br3, where R is an alkyl group, so first of all, it will be sp2 hybridized, right? It will be having a planar structure, trigonal planar structure. When it forms an adduct, it changes to sp3 hybridization. Suppose we are talking about the formation of adduct here, Br3, where it is forming an adduct with the substituted amine. Right. So now if the alkyl group is large, then it can branch off so that the acidic strength is reduced. So now, as a result of all of these, whenever we consider a large molecule, so it can be trimethyl borane, so it is almost inert towards these trialkyl amines, mainly because the planar triangular molecule, the geometry, whatever it has, that is with 120-degree bond angle, so it is forced to make the tetrahedral complexation, the tetrahedral formation, right, during the complexation. So where the bond angle decreases to 109 degree, 109.5 degree. So because of this, there will be too much of crowding, or again, I can say it can lead to the steric effects, right? So due to all of this, what happens is it is forced to fold back. The mesetyl group, you can see that there will be, this group will be forced to fold back. Again, since it is folding here, it is folding behind the carbon atom. We call it as the B strain or the back strain. Okay, so let us look into how the configuration changes here. So B R3. So we know that in the first case, we know this is 120 degree. First of all, it was in the sp2 hybridization. Now, whenever it is forming an adduct, so let us consider Nr3. Now here we have boron and with 3 substituents with the 3 alkyl groups. Now it is forming, so you can see the structure. It is very clear. It is tetrahedral now, and the bond angle decreases to 109.5 degree. So now just imagine when the trimethyl borane is taken into consideration, right? Where you have these this structure. So mesetyl group is nothing but mesitylene. Let us look into the structure. So we have a benzene ring, and here there are CH3 groups. So this is mesitylene. So when such bulky groups are present as substituents on boron, then what happens is the strain, the steric strain increases. So because of the strain that is present here, mainly because of the decrease in the bond angle from sp2 to sp3, the conversion of the hybridization takes place. So here the groups are forced to bend back or fold back. So because of this, we call it as the B strain or the back strain. Right. So now in talking about the amines, so B strain, mainly it results from the structural necessity at the nitrogen, which carries very large substituents. So again, in amines, we know that if you consider R3N, right, it is sp3 hybridized and it is tetrahedral in nature. Of course, one of the orbital will have the lone pair of electrons, but if the substituents are very large, suppose we talk about ethyl, all the 3 substituents are ethyl groups or whatever it is. When we are talking about large substituents, then they are forced to open up. Okay, and in extreme cases, what happens is the molecule may even flatten out. Okay, so in this case, from sp3, it can change to the sp2 hybridized molecule where the lone pair of electron will be present in the p orbital. Okay, so let us look into this in much detail. I'll just show it, I'll write it here itself. So in ammonia, we know that it is sp3 hybridized. So there is a lone pair of electron here and the three R groups, right? So here CH3 is a, now if I consider this R as a CH3 group, so it is a small substituent. So there is no strain as such. So here it will be in the sp3 hybridized form itself. So in this case, I am considering the R as CH3, which is a small group. Now, suppose if one of these R's, if these R groups are taken as large substituents, then what is going to happen? As I already told, here there will be forcing of these R groups in such a way that overall the geometry of the molecule changes. So from sp3, it is changing to sp2 hybridization. Okay. So here, whatever the lone pair is present, it will be present in the pure p orbital. Right. So again, here we need to remember that whenever the substituents are large, so in the first case, we considered only methyl substituent. Here, the substituent is large. So in this case, what is going to happen? Here, the molecular geometry will change from tetrahedral to the triangular planar structure. Okay. So next, talking about the effects of solvents on the acid-base strength. So talking about the solvents, we know that again, they play a very great role in deciding the basicity of the amines. So if you're talking about amines, so R2NH, that is secondary amine, is more basic when compared to the primary amine, that is RNH2, which is again highly basic when compared to that of the tertiary amine. So here, it is mainly because of the solvation of the amines in water. Suppose we consider the gaseous state, then this is the order, that is NH3, which will be less basic when compared to that of CH3NH2, which is again less basic when compared to CH3 twice NH, which is less basic when compared to that of the tertiary amine. So this is in the gaseous phase. And this is in the presence of, due to the solvation, that is in the presence of solvent, this is the order that is observed. Right. So here again, no steric effect is observed in tertiary amines in the gaseous state. So because of which you can see that in the gaseous state, due to the three electron releasing groups that are attached to the nitrogen, there is increased basicity observed in the tertiary amines. But when these amines are dissolved in water, we get NH4 plus ions. Okay. NH4 plus ions are formed. So this NH4 plus ions that are formed, they undergo hydration because of hydrogen bonding. So the greater the number of hydrogen bonds that are formed by the ammonium ions of this particular base amine, then larger will be the heat of hydration. So greater the number of hydrogen bonds formed, greater is the heat of hydration. So based on that, let us try to understand in terms of the structure, how the hydrogen bonds are formed with respect to primary, secondary, as well as tertiary amines. So we know that RNH2 in the presence of water, I told you the ammonium ion will be formed, but now there is a substituent also. So you're going to get RNH3 plus, right? Along with that, there is OH minus that is formed. So now what is going to happen? Now we are talking about hydration. So N, H, R, and there is one more H here, right? And then we also have here what is going to happen. See here, H is present. So it can form a hydrogen bond with water molecule. Here there is one more H. So it can form a hydrogen bond with one more water molecule. Now we know that there is also one more H that is present because NH3, right? So this is positively charged anyways. Now this hydrogen can also form the hydrogen bond with the water molecule. So this particular thing, that is RNH3 plus, in the presence of water molecules. So to balance the equation, I'm writing 3 water molecules. So you can see that this particular cation, it can form 3 hydrogen bonds with the surrounding water molecules. Similarly, this is with respect to the primary amine. So if I take secondary amine, so what is going to happen? So secondary amine, we know that R2NH in the presence of water. First of all, we have to get the ammonium ion. So here there are R groups. So you're going to get R2NH, NH2, and here the plus charge, and along with that OH minus. So let us write the structure based on the hydrogen bonding that is taking place. So R, there are only 2 hydrogen atoms which are attached to the nitrogen. So here there is one more R group. So so obviously this is positively charged. Now this hydrogen can form hydrogen bonding with water molecule. here again, hydrogen bond with one more water molecule. So here you can see it's only two hydrogen bonds that are formed with the ammonium cation. That is, here it is again alkyl substituted ammonium cation. So here, to balance the equation, I'm going to write 2H2O. Right. Now let me write it for tertiary amine. Right. So here we have R3N in the presence of water. You're going to get R3NH here plus charge along with that OH minus. Now, here it is very clear there is only one hydrogen that is present, which is attached to nitrogen, right? So here I'm going to write hydrogen, sorry. So it is hydrogen here. Now we know that here again it is plus charge. This can form hydrogen bond with water molecule. So let me write it clearly here. Yes. So this is how, in this case, in the primary amine, you're going to see that there are three hydrogen bonds that are formed. In secondary amine, only two. Whereas in case of tertiary amine, it is only one hydrogen bond is formed. So mainly, this order of basicity is mainly due to the solvation. So it is entirely opposite to that observed in the gaseous phase. And again, in terms of inductive effect, we observe it. We predict that the tertiary amine is the one which is more basic, but here whatever is observed in terms of solvation effects will be the opposite. So basicity of amines in the solution, it is a combined effect of inductive effect of substituents and also the extent of solvation of the conjugate acid of the base which is formed. So here we have seen how the ammonium ions along with the substituents, how it is formed. So based on that, we have the acidic, we have the basic nature for the different substituted amines. Right. Now talking about the effect of non-aqueous solvents. So basic solvents like ammonia, amides, hydrazines. So all of these, they promote ionization of the acids. So all of the acids, they tend to become strong in case of these basic solvents. Okay. So such solvents, we say that they have a leveling effect for all of these acids. Now talking about the base acidic solvents like acetic acid, formic acid, hydrogen halides. So all of these will strengthen the bases and they weaken the other acids which are added to these solvents. So these solvents, they show a differentiating effect for the acids. So talking about the leveling as well as differentiating solvents based on whatever we have discussed. So water, it acts as a leveling solvent for strong acids and strong bases. So the strong acids and bases, they show similar strength in the presence of water. Relative strengths are compared by making use of the differentiating solvents. So we have two different types of solvents, leveling as well as differentiating solvents. Right. So leveling effect is where you can see that overall the strength is leveled up whenever you're adding the different compounds to the same solvent. Now, differentiating solvents will help you to understand and compare the strength of the various acids or the bases based on which compound you're adding. So acetic acid, it is a differentiating solvent for the strong acids. Right. So as I already told, water, it behaves as a leveling solvent mainly for the acids, such as I can write it as, here are some examples, HClO4, hydroiodic acid, HBr, HNO3, HCl. So for all these acids, the water behaves like a leveling solvent. And also for certain bases, also it acts as a leveling solvent, such as sodium hydride, sodamide. Okay. So for such bases, again, the water is acting as a leveling solvent. Now, as I've told about this acetic acid, it acts as a differentiating solvent towards the various strong acids, especially the halogen acids. So we can see that here the acidic strength is in this order. Right? So the acetic acid, for this purpose, it is extensively used to determine the relative strengths of the strong acids, even for HClO4 or H2SO4, HNO3, even for the halogen acids, etc. So it is found that in the acetic acid, it is found, the order is found to be HClO4, which is most strong in acetic acid. Then we have HI, HBr, then we have HCl, then we have H2SO4. This is in acetic acid and HNO3. But the acetic acid, it acts as a leveling solvent in the bases, okay, for bases. So obviously, when you're taking different types of bases like ammonia or primary amine, secondary amine or tertiary amine, then you cannot distinguish their basic strength in when you're taking them as when you're taking acetic acid as a solvent to test the basic strength of these different amines. Right. So next, coming on to the very important concept, that is Usinovich concept. So this was proposed by Usinovich, and it gives a very broad definition of acids and bases, and it is a more general acid-base concept. It includes all the acids and bases. Again, it is the ones which are defined by Lewis. So those acids and bases are also included here. Along with that, donation or acceptance of electrons, it's not considered only strictly in terms of the electron pairs. So even if one of the electron is donated or accepted, even those reactions are considered as acid-base reactions. So based on this, even the oxidation reduction reactions, that is redox reactions, are also classified as acid-base reactions under this Usinovich concept. Now, based on this, acid is the one which is considered as the compound which reacts with the base, which accepts anions or electrons, and it furnishes cations. So these are the three main characteristics of the acid. Talking about base, it is the one which reacts with acid, it accepts cations, and it furnishes anions or electrons. So this was the basic general definitions given to acids and bases by Usinovich. So now let us consider certain examples of acid-base reactions in terms of Usinovich concept. And let us look at the first example. So SO3 plus, if I take sodium oxide, you're going to get sodium sulfate, which is a salt. So now here, this is considered as the acid and this is considered as the base. And here we know that this is the salt, right? So how do you explain this? Now Na2O, it gives 2Na plus O2 minus, right? Now Na2O, it gives O2 minus, which is the anion, right? It furnishes anion. So therefore, it is considered as a base, right? Similarly, when I take SO3, so SO3 in the presence of oxide, it gives SO4 2 minus. Now here you can see it accepts anions or electrons. So in this case, it is accepting and it is reacting with the anion, right? So here we consider this SO3 as the acid. Right. Coming on to the second example, so Cl2 plus Na gives NaCl, right? So let us balance the equation here, 2Na, done. So let us try to split this equation. So have 2Na in the presence. So here what is going to happen? You're going to get Na plus and it loses electrons. So 2 here and 2 here to balance the equation. So here Na is furnishing the electrons because of which it is acting as a base. So similarly, I can write it for chlorine, 2Cl. Now if I add 2 electrons to this, I get 2Cl minus, right? Because here NaCl is nothing but it is made up of Na plus and Cl minus ions. So 2 Cl minus ions have to be formed. Here Cl is accepting electrons, so because of which it is acting as an acid. So this is acid, this acts as a base, right? So again, here also this particular reaction is considered as an acid-base reaction. So now let us look into the limitation of this Usinovich concept. So it is very clear that under Usinovich concept, we have considered almost all the reactions as acid-base reactions. So that itself is the limitation of Usinovich concept because it is extremely general and almost all the chemical reactions are considered to be acid-base reactions under this concept. Right. So which is not always true. So it's not always true that all the reactions can be considered under acid-base concept. So this is one limitation because of the generalization of the acids and base concept under Usinovich concept. Okay, so with this, we come to the end of this particular video where I have explained about the acids and bases, the different definitions, and also we have studied in detail about the various factors which affect the strength of the acids as well as the bases. And I hope this video is useful. Subscribe my channel for more such informative chemistry related videos. Thank you.